So as we have discussed what are simplexes and simplical complexes in our previous lectures, now we want to move further ahead. So the first thing we want to discuss is polyhedrons. You already know what is a polyhedron. It's a regular shape, let's say in R3. But what we want to do is that we want to define these polyhedrons in terms of the simplical complexes. Okay. So what we know about simplical complexes so far, let's recall that. And we know that a simplical complex is a set whose elements are just simplexes. Now let's say we have a simplical complex K. So we have a simplicial complex K, and any element, let's say some sigma I, which is a simplex that belongs to K, is also a subset of the space that we're working with. So let's say there is some sigma I that belongs to K, and if this sigma I is a subset of some m-dimensional space, for example, you can take m equals to 3, and that would mean that you are talking about a 3-dimensional space. Okay, so in general we write it as R of m. So if this simplex over here is a subset of this Rm, then such kind of subsets are called polyhedrons. Okay, that's how we define polyhedrons in terms of simplexes. And usually when we talk about a polyhedron, we denote polyhedrons as this. Note that it doesn't necessarily mean that it's some sort of a modulus, so please don't confuse it with some modulus thing. And now we want to talk about another thing, that is we want to define something called triangulation. To do that, let's say we have a topological space X if there exists a simplicial complex let's say K, and a homeomorphism which we denote with F, and it's such that it takes the polyhedron and it continuously deforms this polyhedron to the topological space X, then X is said to be triangulable. What this term over here, this triangulable, means is that, so let me use a different color. It means we can break the space up into triangles. And let me show you an intuitive example. So let's say this is a torus, and a triangulation of this torus would mean that you draw a triangle like this, draw another triangle like this, this, and this. So yeah, it doesn't look like a triangle. Okay, so you will have a lot of triangles over here. However, this is in practice a bit difficult, but this example is sufficient enough to get an intuitive understanding of what triangulation actually means. So you are breaking the space up into different triangles. Okay, so this is what we mean by triangulable, and the formal definition of a triangulation is something like this. Triangulation: the pair pair of the simplical complex with this homeomorphism is called a triangulation of X. Okay, so now we introduce some remarks or comments. The procedure to triangulate a topological space is not unique. So the triangulation for a given topological space is not unique. That means you can choose any kind of way to triangulate, or break the topological space into triangles. You can choose any kind of different way, and your end results would be the same. It's independent of this the method that you are choosing to triangulate the topological space. And remark number 2 is that the triangulation procedure breaks a simplicial complex into further components that are also simplicial complexes. Okay, and now we want to focus into something else that is called a orientation, that we talked very briefly earlier, but now we want to get into details, and this will be a bit important for us.